Up next, I'm super happy to welcome Simon Knowles, who's the CTO and co-founder of Graphcore, which is inventing a new processor for the machine learning age. Simon's been in the business for a very long time. He's founded 2 companies, Icera and Element14, were sold for over $1 billion, so he knows what to do here. So over to you, Simon.
Do I look old?
No.
Thank you. So Graphcore is a relatively young company. We announced our existence and our first round of funding last September. We have about 50 people today, pretty much all engineers. We've actually been working on this hardware, I'll say a little bit about, for about 3 years. We haven't released specifications yet, so I'm not going to do a sort of full show and tell, but I'll present some outline and some discussion of the sorts of things that are guiding our mission. In fact, we will make another funding-related announcement very shortly now. We are growing like a weed, so if anyone fancies a career in chips for machine learning, you know where to come. At the moment, we are most famous for producing some eye candy that pops out of our tools. This is ResNet. Layer by layer evolution. You can see some of the stacks of identical layers of convolutional nets go around these loops here. We gain no insight from this. This is just eye candy. This is just bringing joy to the world. But we like it, so we do it and we stick it on the web, and then people say, "But there's nothing there." Yeah, you're right. There's nothing there. So, intelligent. I'm going to simplify a couple of things over the next couple of slides. So anyone who's deep into this technology, I apologize in advance for simplifying your entire world unreasonably, but it will serve to illustrate some points as I go along. So first of all, it's helpful if you're going to build intelligent machines, which is our mission, to have some idea of how you define intelligence. Greek philosophers had a go about 2,000 years ago and couldn't agree, and psychologists have been arguing ever since. Most people in the psychology world think there are 3 forms of inference: induction, deduction, and abduction. And even just last year, there was a conference on whether induction and abduction are in fact the same thing. And the conference did not conclude. So, so there is no definition of intelligence, but this is my approximate definition for the purposes of building machinery. So I characterize it as the capacity for judgment, rational judgment, based on imperfect knowledge, which is adapted with experience. So you've captured the important things here. In particular, that there is always a knowledge base. That knowledge base is always, to some extent, wrong. And without learning, then there is no intelligence. Without imperfection, there is no intelligence. If you built an autonomous car and it crashed, and then you gave it exactly the same scenario and it crashed in exactly the same way, you wouldn't regard it as intelligent. So there has to be some learning component. And as we know, learning is just forming a condensate of experience as far as a machine is concerned. And that experience is just data. So we're just compressing data. And here's my simplest possible diagram of an intelligence machine. So it has 2 parts. There's an inference engine and there's a knowledge model. Notice that there's no learning box here. Much is made in the world of GPUs and other rival silicon about whether chips are for training or for inference. I'd like to make the point that there is no fundamental distinction there. Learning is just inference of model parameters or model structure. And so I think in order to build general machines for intelligent action, it's helpful not to think of a distinction. In fact, it's hard for me to imagine that when we deploy intelligence in machines in the world, we will not want them to some extent to incrementally improve their behavior. In other words, there will be no large-scale market, I believe, for pure inference. Well, you can read the labels. Here's some more eye candy, just to keep you awake, if the hunger pre-lunch isn't doing that automatically. So, as you all know in this room, knowledge models and the algorithms required to perform inference on them are most naturally captured as graphs. They're very high-dimensional structures. If everything was connected to everything else, then that wouldn't be tractable. So they are intrinsically sparse. And from a machine designer's point of view, in particular, the model structure is generally static, or at least it's static over long periods of time. I'll come back to that because that's a really vital characteristic when it comes to designing efficient machines to do this sort of computation on these sorts of models. So in those graphs, the vertices, they capture the state of the model, parameters, activations, etc. And the edges are stateless, and they have direction. So they are, to some extent, causal. And computing on these kind of models is actually fundamentally new. I've been building processors for various applications, as have many in my team, for about 30 years. I've never seen a workload that looks like this one. Some of you will say this is more than one, but I'll come to that. And one of my guidelines, if any of you ever think of starting a chip company to make processors for anything, this is my first piece of advice, my only piece of advice. Don't even think about it, because unless you can see forward, or at least you can try and see forward 20 years. Building a processor is difficult, but building all the software on top of it to make it useful is even more difficult. And unless it's going to be useful for 20 years, then you're probably not on the right path. So who's going to bet what we'll be using in 20 years' time? If we had asked that question in 2005, you probably would have built a machine to do support vector machines. That would have been your focus. 2010, probably random forests. I like to point to the Microsoft Kinect as the first mass market consumer inference engine. It uses random forests to work out where your body is and how well you're dancing. If that was designed today, do you think they'd use random forests? I don't. I think they'd throw neural networks at it, to be honest. So it was a child of its time. And if you'd built a processor for machine learning following fashion then, you would have built something for random forest. Now it's neural networks. 2025. Anyone get the interocitor reference there? Come and see me afterwards. Very famous story, 1949, I believe, which led to the classic sci-fi movie, This Island Earth. The interocitor is a magical machine that does all sorts of things, including intelligent behavior. But the point is, if you're going to build a machine today to do intelligence processing, then do not build it just to do neural networks. And we are not building a machine just to do neural networks. However, neural networks are clearly important, as are random forests, as are SVMs, as are all the other things that we have learned. So it has to do all those, but it has to think more fundamentally. And the first question to ask is, what are those fundamentals? What is fundamental about the machine intelligence compute task as a workload? And here's my list, or a list. You could go on forever, but huge parallelism. Obviously, these are massive high-dimensional models. They are intrinsically sparse, but also because they're high-dimensional, if we embed them in low-dimensional memories, which are the only ones we can make, then you will induce further sparsity. You can't have 1 million nearest neighbors in a one-dimensional address space. They are intrinsically stochastically learned and approximate. So parameters and values in these models during this computation will be low precision. This is probably the first application that we have come across for very high performance compute on very low precision data. It's completely the opposite of traditional HPC, as it's called. The reuse of model parameters is clearly emerging as fundamental. That's what convolution is all about, spatial reuse. And recurrence is all about reuse over time. And if you reuse your parameters, then you expose them to more data, you learn them faster, etc. So that's probably fundamental. The static nature of the graph. Now, this is a really contentious one. There are some people who think that we need to build machines that deal with evolving model structure. I point to the axons and neurons in your head, which do not rewire as you think. They can rewire very, very slowly with exercise. Or indeed the Ethernet cabling in a data center, which you do not rearrange when you change your applications. You may, of course, have vertices that perform a routing function, so you virtualize a changing network. That's a different story, so that's fine. But the network, the graph structure, is static, and this means, crucially, that the 3 NP hard tasks that we have in mapping a graph to a parallel machine can be done by the compiler. They don't have to be done by the machine. And they are partitioning of work, the allocation of memory, and the scheduling of messages. The others you can conjecture about. Sources of entropy is probably an important one. Without the ability to conjecture, you can't do induction or abduction in traditional philosophical world. So I think there will be new machines. We have decided in Graphcore that they should be called IPUs. Google have decided that they should be called TPUs. Google's bigger than us, so they'll probably be called TPUs. They may be called something else, I don't know, but they're not the ones that we have so far. CPUs were designed for scalar workloads. GPUs were designed for low-dimensional vector-type workloads, two-dimensional images, three-dimensional volumes. These machines for intelligence will be designed for high-dimensional graphs. They will have completely different characteristics. Today, of course, we all use GPUs. It's the best that exists. But I assure you, Graphcore will not be the only people who build something else. So what might limit the performance of such a machine? The rate at which we can do arithmetic, data access, the rate at which we can generate addresses in a sparse context, all these things, yep, they are all going to limit the performance of a machine. But there's one thing that's going to limit. Hey, how about that? That slide went wrong. That's supposed to be at an angle, never mind. There's one thing that's going to, I hate PowerPoint. One thing that's going to limit the performance of a machine more than anything else, because it limits all digital silicon today, and that is power. We can build a silicon chip, fab optics limit of about 8 square centimeters. Biggest chip you can make in any fab in the world. Big enough for about 25 billion transistors. It's quite a toolkit. And we can feed it with about 200 watts. And we can extract about 200 watts of air without getting really fancy with liquid cooling and that kind of stuff, which is increasingly coming. Just to feed that chip with that sort of power requires the kind of current that your car battery supplies to the starter motor when you start your car. And that has to run through the tiny little pins on these packages. It's a hell of a engineering feat. 1/10 of a milliohm of supply resistance is about all you can tolerate. Now, if we're going to do arithmetic with this chip, here are some relevant numbers. If you're going to do build 64-bit floating point units, you'll dissipate about 32 picojoules per tick, where a tick is maybe 2 flops, a multiply add. And you can fit about 15 in a square millimeter. That's probably not very important for machine learning. We're at the low precision end. So the float 16, the little 16-bit floating point units, about 250 per square millimeter, and about 2 picojoules per cycle. Now do the maths, that's about 50 watts per gigahertz per square centimeter. That means at a typical, sensible, for today's technology, 1.5 gigahertz, you can only put about a third of your die you can fill with floating point units. In other words, if you fill the whole die with these things, to do the maths, you can't run the thing at full speed. You can only run it about a third of the speed. So you end up with this dark silicon phenomenon. It's a fundamental power limit. Before I get on to what to do with that, let's talk about the memory side, because obviously we've got to feed these floating point units from memory. Today you have 4 choices. External DRAM outside your thermal envelope, typically DDR4 modules. Not much bandwidth available, you've got to get off the chip. The second one in, a new technology, high bandwidth memories. These are memories put very close to your logic die on a silicon substrate, and actually they're vertically stacked, multi-die stacks. And that's what today's state-of-the-art GPUs are using. This is heroic technology, frankly. Incredibly complex, incredibly difficult to manufacture reliably. We're edging towards a terabyte per second. Or you can just live with the memory that you could fit on the chip. So on the chip you can use static memory, as it's called. You can't fit anywhere near as much as you could with off-chip DRAM in one of those 2 other configurations. But you can fit maybe 1/4 of a gigabyte. And so your choice there is, do I put it all in one pool and address it as such, or do I split it up into lots of little pieces and have lots of little processors dealing with individual pieces? Whichever you do, you can get orders of magnitude higher bandwidth for the same power budget to your logic. So that's quite interesting. So there's a trade-off to be made here. Could you deal with models which lived entirely on the chip, that had less memory available to them, but that memory was far, far more accessible to the arithmetic for the same power budget? And as I've said, power budget is what limits. And in fact, the power density of memory used in these on-chip configurations leads to roughly a quarter of the power density of doing the arithmetic. So they're about 4 times the lower power per square centimetre. So you end up with these two plans. The one on the left is what the GPUs do. They can't use all of the logic on the die, and the memory for them, most of the memory is off the die. So they have dark areas. They cannot power everything. So what do? They use that area for other markets. If you buy a GPU today, it is designed for 3 markets. It's designed for graphics, it's designed for high-performance computing, and now it's designed for machine learning. Whichever one you use it in, you're only using part of what's on the die. It's quite a nice economic model. I make 1 chip, I sell it to 3 different communities of people. The stuff that's on the die, of course, that you are using in any one application uses most of your power. There is the other plan, and this is the IPU plan. This is what we're doing. So in this scenario, you say, okay, I'm only interested in machine intelligence. So I'll put down a little bit less logic on my die, and because I can run memory at a lower power density, I can actually fill the rest with memory, and I can use the whole thing. So in other words, I have a memory-centric die. The die is mostly memory. And I get to use all of my power. Doesn't do graphics, doesn't do HPC, just does machine intelligence. So I got this new definition of what it means to be efficient. We used to think of efficiency as using all the stuff on your chip at the same time, as much as possible. But that's not true anymore. The metric of efficiency now, since we became power limited, which is about 12 years ago, is using all the power available all the time. I've talked about doing that by helping to keep the memory local, so the access energy to the memory is low. There are 2 other things we can do to help this. One is we can serialize communication and compute. Now this sounds really weird. You would think, if you're trying to be efficient, that you should overlap communication between processors at the same time as compute. Actually, it's more efficient in a power-limited world to serialize them. Surprising, but I'll show you why. And then the third thing you can do is you can trade computation for, recomputation for storage. If you look at those numbers I showed you earlier, it takes far more energy to get the values out of a memory, even if it's very close, to do some arithmetic on them than it does to do the arithmetic. So actually it can certainly be more efficient to recompute a value than to save it away and recover it. This business about serializing communication and compute. On the top row here, I've shown what we used to do. This is what we used to regard as efficient. You would allocate your power according to some design budget between compute and exchange, which is communication between processing elements on your chip. Now then, when you actually came to use it in an application, suppose that ratio was different. You were limited in terms of throughput to the same time, either in this case by the amount of communication bandwidth available, and you've underused the compute piece. So what you've done is you've saved power. Now if you'd serialized them, which is the bottom row, instead of saving power, what you would have done is saved time. In a power limited scenario, that's what we want to do. We get to use all of the power available, and we get the answer to our program earlier. There is a catch, and that is that if the compute is being done by lots of little processors all cooperating, they all have to be very well load balanced. They all have to have roughly the same amount of work, so they can all finish at roughly the same time, and then they can communicate. And that is a question of, is that a characteristic of your workload? Actually, it is a characteristic of this workload. So, an IPU style machine, we've slightly trimmed that diagram as well. An IPU style machine is a pure distributed parallel processor, so that we can build little ones and big ones, and in future really, really big ones, and it will still be the same machine. So it consists entirely of lots of independent little processors with their own little memory that can send messages to each other through a completely stateless, perfect interconnect. Because there's nothing shared, there's no shared scheduler, because that's done by the compiler. There's no shared memory, because that's not scalable. So we can build this machine of any size we like. And how do we make the processors, how do we allow the processors to communicate with each other safely? If you imagine you've got a program, you've split it into 1,000 pieces to put on 1,000 little machines on your one silicon chip, and they all want to send messages to each other. They have to have some collective idea of what time it is, so that they know roughly where they are in each other's programs. Now, there is a paradigm for doing that. It's called bulk synchronous parallel. It was invented in 1990. It was evaluated and did not become fashionable because it requires that you alternate between phase of compute in which everything just happens locally. So every little processor just does compute on its own local memory. And then when they've all finished, everyone synchronizes. In other words, everyone agrees that we've finished, and then they all move to a communications phase, usually called an exchange phase, where everyone just sends messages between their memories, but they don't do any compute. And then when they've finished sending messages, they go back to compute, and you go around the loop again. And the whole machine operates like this. It ping-pongs between compute and exchange. Notice we're serializing compute and communication as per my previous description. Now, why didn't it become fashionable? Well, because synchronization off-chip is very expensive, takes a long time, and because the kind of bandwidth that you would ideally require to do all of that simultaneous communication is also super expensive off-chip. But here we are, 27 years later, with 25 billion transistors in our toolbox on one silicon die, we can now build something which will support 1,000 processors running at a specification I can't yet release, but faster than any GPU today. And you can do completely non-blocking communication in that exchange phase from any processor to any processor in any pattern all the time, changing every cycle. Couldn't have built that previously. It takes miles and miles of wire, which you have to cram onto your little chip. But this is okay. Right, so the other thing I mentioned was recomputation instead of storage. There are basically 4 things that constitute state in an intelligence processor: the structure of the graph, the parameters of the graph, the parameters of the model, the persistent data, which is the parameter of the model, the vertex code, which is what the model should be doing at each vertex, and ephemeral data, model activations. And I've said if you're going to build an IPU system, then what you've got is a smaller memory, but much greater compute. So you need to trade these two. And there are 3 things that you can do, obviously, to reduce the memory consumption of a GPU. GPUs require large batches, IPUs don't. GPUs have to lower convolutions to matrix multipliers because that's the low-dimensional structure they're built to execute. IPUs don't. They can implement quite complex convolutions directly. And this business of recomputing ephemeral state, there's been a lot of research on this. I just pointed 4 papers there, but there are many more coming out. And here is final kind of technical picture. So this is a chunk of a deep neural network, a bunch of activations on the top line, a bunch of weights in orange in the middle, a bunch of gradients along the bottom line. And obviously in training you sweep along the top, left to right, and then you sweep back along the bottom, right to left. And 3 phases: forward, backward, and then weight update. In a scenario where I want to minimize computation, I save all my forward activations because I'm going to need them when I go backwards. But in a recomputation scenario, I only save one every now and then. Then when I go backwards, I have to recompute forwards for that chunk to the next one in order to do the backward propagation. So what it means is I can save most of my activation state, which is most of the state of the model that's not parameters. I can save most of that for the cost of doing that forward sweep twice, which is typically maybe 30%. So 30% more compute, I can save 1 or 2 orders of magnitude of memory, typically. So that's how you close the gap between a gigabyte, multi-gigabyte GPU system with external memory and an IPU system that only has a fraction of a gigabyte on the chip. So last slide, tell you a little bit about our machine. Colossus is an internal name we use in honor of Tommy Flowers, the architect, designer of the first electronic computer in December 1943, it first ran. We have not released the specifications of our Colossus yet, and when we do announce the product, it will be called something else. So Colossus is our engineering name. It's designed from the ground up for machine intelligence. I think we will see other chips with that mandate, but this is certainly the case in our case. So it's not a GPU being adapted to something else. It's nothing like a GPU, as I hope I've given you a little bit of insight into. It's a very large, state-of-the-art 16 nanometer FinFET chip, very large. And we put 2 of those on a PCI Express card and bolt them together. It's designed to be clustered into arrays, but our first product, we put 2 on a PCI Express card, and that's equivalent to buying a GPU card. You could plug it into the same socket, and you can run the same software that you've written in TensorFlow or something like that. It'll just run faster. Same power budget, same physical form factor. Each chip has more than 1,000 processors. Compare that with current Pascal GPU has 60 processors. So this is order of magnitude more processors, each independently running a program. All the model state remains on the chip. There is no external memory. This is a very radical, different kind of design, and centers on mixed precision floating point, 16-bit floating point for multiplications, most multiplications, and 32-bit accumulations. We've seen the same move made recently by NVIDIA's Volta and also by the Google TPU2. So I think the world is kind of converging on that kind of arithmetic. Its performance we have not yet announced, but it will be well beyond the NVIDIA Volta and well beyond the TPU2 card with 4 chips on it. And it does not require large batches to achieve that performance. It can operate with very small batches. It also, we hope, is a lot more than just a machine for doing neural networks. As I tried to highlight at the beginning of the talk, this is supposed to be capturing those fundamentals. It's not a machine specifically for neural networks, but it will outperform today's machines on neural networks. As I mentioned, you program it in TensorFlow. Other frameworks will follow. We also have a lower level framework for stuff that doesn't fit into the idiom of those higher level frameworks. And we will show our first hardware machines at the end of this year. Here is some more eye candy. Thank you. These are all real neural networks, by the way. This one is some sort of LIGO simulation. I can't remember exactly. It's a small piece of it.
Question on the left. Question on the left.
I have a question. Hi, it's Luc again. Yes, hi.
Hi, Luc.
These processors, how do they synchronize? Is there one big cycle where everybody exchanges, or is there inter-processor synchronization?
It's bulk synchronous, so whether it's on one chip or on a cluster of chips connected together, everyone simultaneously moves from the compute phase to the exchange phase. And
so then how do they all know that they're ready?
They finish the program. They finish their work. Now, how do we know that the work's all going to finish at the same time?
It's upfront.
The compiler knows, because the entire machine is deterministic. No caches. Threads are used to hide tricky latencies, all sorts of stuff.
Yeah, exactly.
Can you have one? You can later.
Peter from Facebook. 2 questions. The first, could you explain what those eye candy graphs in the very beginning actually were? I didn't really. And the second question, just as a hardware startup or company, how do you manage to stay agile? Because anything you do right now, maybe in 2 years, the research community has moved on and you already bought 1 million chips. So how do you capture the current trend, but also plan for 20 years ahead, like you mentioned?
Well, it's a punt. Like I say, we try not to capture today's fashion. We try to capture the sort of list of fundamentals in the behavior of our machine, which I mentioned at the beginning. There we are. That's what we bet on. So we've built a machine with those characteristics. None of that says neural networks, but obviously neural networks do fit in with that. What are the eye candy shots? So what we do is we take a TensorFlow description of a neural network. This one is AlexNet, very familiar to all of you, I expect. We give that, so TensorFlow will give us a graph. You capture the forward graph, it will augment that to provide the backward backpropagation graph and the weight update. So we get that graph from TensorFlow. That graph does not have enough parallelism, really, for a machine of this scale. So we take tensor volumes and split them up into pieces and allocate different pieces to different processors. So we build essentially a finer grain graph from that. And this is what happens if you give that fine grain graph that's got maybe a million nodes or 10 million nodes to a graph layout tool and tell it to optimize for routing length in a circle. So it provides not much insight, as I said. But, we bring joy to the world. What's wrong with that?
Nice. Simon,
Yeah.
Heath Terry, Goldman Sachs. Just
Hi.
curious if you can give us a sense sort of what kind of production levels you're expecting, how quickly you can sort of scale, and how you expect to handle the production and demand side of things.
I wish I knew. Everyone in this room knows that predicting the future is impossible. We have a variety of pre-customers. We don't have hardware yet, so we don't have any actual customers, but we do have a lot of pre-customers, and they're quite a rich mix. Some of them think that they are going to require us to scale extraordinarily quickly, and others, of course, are more modest. This is a new technology. People will take a while to get used to it. Can we scale fast? We have an engineering team that has, I said today it's 50 strong. By the end of next year, it'll be about 150 strong. Today, it has an average experience per engineer about 18 years. So these are guys who have done this sort of business before. This is my 8th new processor architecture from scratch for a different application. Many of the others in the team have a long history in building new processors for new applications and scaling businesses behind them. So if you like, we have the skill set. But if it takes off like we hope it will, then we will be challenged. We are fabless, of course. We're not going to build our own fab for the avoidance of doubt.
Maybe one last question.
Over here, Johnny Singh from Fidelity. How much of this can be done with an FPGA? Because I guess dividing up the configuration of the compute units is something you could, in theory, do with a PLD. Is the memory cell or the ability to put that onto the die a restriction in terms of FPGAs applying this type of approach?
So I get asked questions about FPGAs all the time. FPGAs consist of kind of two halves. One half is some hardened custom structures for certain types of arithmetic or memory or IOs, depending on what the application target of the FPGA is. So in other words, there are very few pure FPGAs anymore. They're mostly application focused. And then the other half is a sea of configurable logic. The sea of configurable logic is inefficient by multiple orders of magnitude compared with building the logic. So if you do anything in that sea of configurable logic, you are maybe 1,000 times less efficient than if you had built a chip. So an FPGA only makes sense if you don't know what you want in hardware at the time that you build it. This is not in that space. We do know, at least in broad brush terms, what we want to build. So in terms of why don't we do this in FPGA, well, you could not fit more than 1/100th of the arithmetic, you could not fit more than 1/100th of the memory, and it would consume about 100 times the power if you attempted to do so. So it's a very, very inefficient platform, flexible in some applications. I have a belief that the FPGA fits in a server in one place going forwards, if at all, and that one place is security. Because security is one of those cases where you may think you know what you need in hardware, and then in 2 years' time someone cracks that algorithm, and without replacing all of your servers, you need to implement a new algorithm, and that's where you'd be glad you had an FPGA, but not here.
All right, great. Let's thank Simon.